Let's get started talking about Chapter 10, Crustal Deformation and Mountain Building. And this is where I hope to show you some of the things that plate tectonics does to create the landscape that we see around us. What causes rocks to deform? Deformation is a general term that refers to the changes in the shape or position of a rock body in response to differential stress. Now you might have thought that stress was something that was exclusive to human experience, but rocks experience stress too through pressure and temperature and things like that. Most deformation occurs in association with plate boundaries. So where you have a converging plate boundary or even a diverging plate boundary or even a transform boundary, there is stress that is happening along the rock lines. And in fact, this is related to a lot of the earthquakes that we talked about in Chapter 8. Resulting rock structures are categorized as folds, faults, and joints. When the stresses acting on a rock body exceed its strength, the rock will respond in several ways. It will either deform by folding, by flowing, by fracturing, or by faulting. And we're going to go through most of these in the next few moments. There are several things that cause stress. Confining pressure occurs when stress is applied uniformly in all directions. Stress that is applied unequally in all directions results in differential stress, and there are three types of differential stress. When a rock is squeezed like in a vise, it's called compressional stress, and this is most often associated with convergent plate boundaries because the plates are being pushed together, and so the rock is being forced to expand vertically, both downward and upward. Tensional stresses are stresses that pull apart or elongate a rock body, and this happens most often with a divergent plate boundary. A good example of this is where even where a plate boundary is trying to form, such as in the rift valleys of Africa. And shear stress is when one part of the rock is being stretched past another part of the rock at the same time. So this is quite common along transform plate boundaries, such as the San Andreas Fault of California, where the Pacific plate is rubbing up against the North American plate. And so here we see all of these stresses illustrated here. You see the confining stress, the pressure in all directions. So if that rock body, in theory, was able to melt, then it would probably become more dense in response to that confining stress. Intentional stresses, it's just like where, somebody's grabbing your legs and your arms and trying to stretch you apart a bit. Compressional stress is like the confining stress, except that it's only from a certain direction, and so the rock body will tend to expand in the directions that are not where the pressure is not being applied. And then the shear stress, you can see how that causes the rock body to warp. And if you look at a lot of geologic formations, especially metamorphic rocks, you'll see that shear stress effect. Now, there are several types of rock deformation. So rocks do not respond the same way at any given time to these stresses. It depends on the temperature, the pressure, the rock type, and how much time is involved. Gradual application of stress may result in elastic changes to a rock. When the stress is released, like a rubber band, but more slowly, much more slowly, the rock will return to its original size and shape. This is called elastic deformation, just like a rubber band is elastic. But just think of this as a much slower process. But if a rock is pushed past its elastic limit, and that's going to be based on its properties, it may fracture, breaking into smaller pieces. And this is where we find faults and joints, which we'll talk about more in a moment. And then you have ductile deformation. This is when a rock slowly changes its shape without fracturing due to stress. So you might think if you put two solid objects and put some putty in the middle and then watch the putty change shape, that would be ductile deformation. Many factors affect rock strength, temperature. Rocks that are hot tend to soften and deform by folding or flowing, but if the same rock is cold, it will most likely fracture. Pressure also makes rocks stronger and harder to break. The rock type also makes a difference because rocks containing minerals that have strong chemical bonds tend to fracture when they are stressed. And then time is a factor. Rocks tend to bend and flow when stress is applied slowly over long periods of time. So I want to talk about folds and ductile deformation, which are related to these stresses. These are rocks that are bent into wave-like undulations called folds, kind of like if you crunch something together like an accordion, basically. This is what happens to some rocks when they're being compressed. Most folds result from compressional stresses that result from the shortening and thickening of the crust. So this would be with like a converging plate boundary. Each layer of a fold is bent around an imaginary axis called a hinge line, or simply a hinge. And these folds are described by their axial plane, which is a surface that connects all the hinge lines of the folded strata. And so those would be the low areas there, and how the geology there is folded in a downward manner. The limbs are basically the sides of the anticlines and the synclines that connect all of the hinge lines of the folded strata. These basic folds are described as symmetrical when the limbs are mirror images of each other, and asymmetrical when they are not. And sometimes a fold becomes so warped by these geologic stresses that it becomes an overturned fold, in which one or both of the limbs are tilted beyond the vertical. And this is a situation where you can actually have older strata that overlies younger strata because it's essentially been moved upside down from its original position. So here in this diagram at the bottom you see a symmetrical fold there on the left. In the middle you see an asymmetrical fold where it's pushed over to the right, and then finally an overturned fold where some of the right limb is actually underneath younger strata of the left limb. And this is a type of geology that you will see quite commonly in the Ridge and Valley provinces of the Appalachian Mountains. Now, another feature associated with these are domes and also basins. A dome occurs when an upwarping produces a circular or slightly elongated structure. So in a dome, once it's eroded flat, in this case, you have the oldest rocks there in the center of the dome and the youngest rocks on the outside. And the downwarping basins are just the opposite. They have a saucer shape, and if they're eroded flat, then the youngest rocks will be in the middle and the oldest around the edges. Now, I don't have that pictured here, but a monocline is another term that is used, and this is where you just have essentially horizontal strata that's been pushed upward in kind of like a stepwise fashion in some area, but otherwise it's flat. Now let's talk about faults and joints for a few moments. A fault in geology forms where brittle deformation leads to fracturing and displacement of the Earth's crust. Some faults are very small and others stretch for hundreds of miles. So you see in the picture here, these are sedimentary strata that were once laid down exactly parallel to each other, but then once these lithified into rocks and were uplifted, the stress on the rocks created these faults. So you see a fault there on the left side in particular, where that dark brown strata has been pushed upward on the left side relative to the same strata on the right side. Now, large faults often consist of many interconnecting smaller faults that are called fault zones. And there are a number of types of faults. The first one I want to talk about is the dip-slip fault. This is a fault in which movement is parallel to the inclination or dip of the fault surface. And thus it is a dip-slip fault. So essentially think of this as more or less vertical movement here of one side of the fault's rock relative to the others. The rock surface immediately above the fault is called the hanging wall block, and the surface below the fault is called the footwall block. Now these terms come from the mining community originally. Vertical displacement along dip-slip faults tends to produce long, low cliffs called fault scarps. Now, a dip-slip fault is called a normal fault when the hanging wall block moves down relative to the footwall block. So normal faults are often associated with tensional stresses that pull rocks apart. So we're referring more to a diverging plate boundary or a plate boundary that's being stretched. Fault block mountains sometimes result from these types of tensions and forces. Now, another type of fault, a dip-slip fault, is still a dip-slip fault, but it's called a reverse fault if the hanging wall block moves up relative to the footwall block. Now, there's also a special case of the reverse fault, and that is if the angle of the fault is less than 45 degrees, it is called a thrust fault, because essentially a block of rock is being pushed up on top of another block of rock. Some thrust faults have a hanging wall block that is nearly horizontal over the footwall block. And thrust faults are common along converging plate boundaries because everything's being pushed together. A good local example for me of a thrust fault, the area in the western Smoky Mountains around Cades Cove, you have some old thrust faults, and because of that you have some older strata that's overlying younger strata, which is the opposite of what is normal. Now, another important type of fault is called a strike-slip fault. And this is a fault in which the dominant displacement is not vertical along the fault line, but it's horizontal. And it's parallel to the direction of the fault surface. Perhaps the most famous example of a strike-slip fault would be the San Andreas Fault in California, where the western edge of California, west of that fault, is being pushed northward relative to the remainder of California and North America. So, as you might have surmised, these types of faults are often common with transform plate boundaries, where one plate is moving against each other, but they're moving past each other, but one is not being subducted under the other. Now, one of the most common rock structures are fractures called joints. Joints are fractures along which no significant displacement has occurred as a fault would have done. Columnar joints, a special type of joints, form when igneous rocks cool and develop shrinkage fractures. Now, a good example of this is if you had a pond and then the pond dried up and the mud at the bottom, creates all these nice little patterns where all the little pieces shrink apart from each other. That's what's going on here with columnar joints. There's also a special type of fracture called sheeting fractures that produce curved joints that form roughly parallel to the surface of large igneous bodies. So the picture you see here is an example of an igneous intrusion, Devil's Tower, Wyoming, and it was made famous by the movie Close Encounters of the Third Kind. Now let's talk about mountain building for a few moments. Orogenesis refers to the processes that collectively produce a mountain belt. Compressional mountains form when great tectonic forces have shortened the crust horizontally while thickening it vertically. Folding and thrust faults are very common features associated with this process, along with metamorphic and igneous activity. One type of mountain building is called the Andean type, and it's named after the Andes Mountains in South America because they're a classic example of this type of mountain building. And this involves the subduction of an oceanic crust beneath a continent rather than another oceanic crust. And subduction in these active continental margins is associated with long-lasting volcanic activity that builds continental volcanic arcs. So if you were to visit the Andes Mountains in South America, you would find that there are many volcanoes among those high mountains. And most such active margins like this were once passive margins. Now, along with this type of activity, we have something called the accretionary wedge. As a volcanic arc develops, unconsolidated sediments and fragments of the ocean crust that are being subducted, parts of that become plastered on the edge of the overriding continental plate. In other words, they're left behind and they don't get subducted. This results in a chaotic accumulation of deformed and thrust faulted sediments that are called the accretionary wedge. Some accretionary wedges do rise above sea level. And a good example of this would be California's coastal ranges, which represent the low mountain ranges along the coastal areas of California, including the San Francisco Bay Area. This area represents a former accretionary wedge. Now, in general, collisional mountain belts are formed when one or more buoyant crustal fragments collide with a continental margin as a result of subduction. Because continental fragments are too buoyant to be subducted, the arrival of the continental fragment at a trench usually ends further subduction. So this is really important because this tells us how some plate boundaries change, because we know that through geologic history, sometimes the continents are moving apart, sometimes they're coming together to form large supercontinents. How does that change? Well, this is one of the processes that affects that, because if you have a continental fragment that's being moved across the ocean by plate tectonics, when it reaches that subduction zone, because it's a continental fragment, it doesn't sink and it stops the subduction in that area. Now, I want to describe what a terrain is, and I'm not talking about a T-E-R-R-A-I-N, but a T-E-R-R-A-N-E. Terrain, in this case, describes crustal fragments such as microcontinents, island arcs, or submerged ocean plateaus that have been transported across the oceans by plate tectonics, and these are the things that sometimes end subduction. Japan would be an example of an island arc like this. Madagascar would be an example of a microcontinent. There are many submerged ocean plateaus under the ocean that fall into this category as well. And accretion is the process by which terrains are added to a continent through plate motions. And orogenesis, as I described earlier, is associated with this, and this is referring to the development of mountains. Many of the terrains that now make up the North American mountains, the ones in the western United States and in western Canada, Alaska, and Mexico, many pieces of this large and long mountain range, the Rocky Mountains, of course, is a major part of that, were once scattered microcontinents and island arcs throughout the eastern Pacific that were moved eastward by the Pacific Plate or its predecessors and then pasted onto North America. So this is one way that continents grow. There's also an alpine type of mountain building, and this occurs when two continental landmasses collide or when island arcs and microcontinents merge with a continent. So examples of this would be the Alps in Europe, the Appalachian Mountains, the Himalayan Mountains in Asia. A perfect example of that today is the Himalayas, because it's being created as the Indian subcontinent has moved northward across the Indian Ocean and collided with Asia. And since both India and Asia are continental crust, they won't sink. And so the collision is just pushing up the Himalayan mountains higher and higher. And that process is actually still going on today. Now, I also want to mention the Appalachian Mountains. They're a very old mountain range, but have a very interesting and long developmental history. Now, about 250 million years ago, you had the supercontinent of Pangaea. So Europe, South America, Africa, Asia, most all of the continents were together as one major continent. So prior to that, you had an ancient Atlantic Ocean, but then this began to close. But inside that ancient Atlantic Ocean was a microcontinent called Avalonia and a volcanic arc called the Taconic Volcanic Arc. And if you're sharp, you might realize that means that there were subduction zones in the Atlantic Ocean where there aren't any today. Then you had the Akkadian orogeny, which is the first real mountain building phase, where the second rather, where the Avalonian microcontinent is added to North America, creating more mountain building after the Taconic mountain building phase. And then the third phase of the Appalachian mountain building was the Alleghenian orogeny, which between 250 million and 300 million years ago, this is where Africa and North America collided, in the final stages of creating the Pangean supercontinent. And this created even more mountain building. Now finally, when this all reversed and the North Atlantic began to form with the Mid-Atlantic ridge in the middle, a piece of coastal Africa was actually left pasted to the North American coast. So if you are ever on the at the beach in the Carolinas, you may want to think about the fact that some of that land you're standing on was actually a part of Africa at one time. So here you see what I've been describing illustrated. You see in the top diagram you have two subduction zones in the Atlantic. You have the Taconic volcanic arc, the Avalonian microcontinent in Africa way there on the other side. And then you see where the Taconic volcanic arc merges and creates the first mountains of the Appalachians. The Atlantic continues to shrink, and then in the second phase you see the Acadian phase where Avalonia is added to North America and creates more mountains. And you can see there that both of the subduction zones associated with those small continental masses are now inactive, becoming inactive, but there's one subduction zone still there that's causing the Atlantic to shrink. And then finally, when Africa and North America collide, you get a major mountain building episode. And then at last, you have the development of the new Atlantic as Africa and North America move apart, with the little piece of Africa left attached to North America. Now, one last thing we want to talk about before we close this chapter is the principle of isostasy. During the 1840s, researchers discovered that the relatively low-density crust, continental crust, floats on top of the high-density mantle. And that's to some extent true of the oceanic crust, but especially the continental crust. This is called isostasy. And mountain building involves the buildup of continental crust both upward and downward. So you might think of just as the way that you see a tree growing upward and you know that there are roots growing downward. The same is kind of true for mountain ranges especially. As a mountain range slowly erodes, the range also slowly rises to maintain its floating balance, if you want to think of it that way. This process also occurs when continental glaciers melt, because when you have continental glaciers, they're kind of like a mountain range. Some of them 2 or 3 miles high. They push down the crust underneath them in the same way that mountains expand the crust downward. So here you see the example of a mountain range, and you can see that how much thicker the crust is in the middle of the mountain range. But as the mountain range erodes down, then there is also uplift underneath the crust that's balancing out this floating, if you want to think of that as of the continental crust. So by the time the mountain range is eroded away, then you have pretty much a uniformly thick crust again. This is probably the cause, if you're like me and you live in the southern Appalachians, you know, we don't have that many strong earthquakes here, but we do occasionally get some very weak ones. And I think one of the reasons for those weak earthquakes is this process of uplift that's going on as the Appalachians erode down. They are also being uplifted from underneath to maintain this balance of isostasy in the crust. All right, well, that's the end of Chapter 10.